Hi, my name is Charlie Sheffield, and I'm going to be discussing my project on optical trapping. Now, science fiction has always given us an example for what the future of science could hold, and I was looking at some science fiction. Some of the science fiction ideas that I was looking at were the Tony Stark Iron Man table and the Princess Leia recording, and these are synonymous with the science fiction realm. And I was looking at how people have in the world have tried to recreate these science fiction phenomena. Now, these images of light look like holograms. They're very three-dimensional holograms that are different than a 2D hologram you can only see on a screen. These ones you can see from all angles, which is very challenging to create. However, this technology has been found before in something called optical tweezers or optical trapping, which was first used in a biological field, and then was applied to physics, which we will talk about in just one second. So a first study was done by Newman and Bloch, and this was a biological study where they would trap small objects inside of a laser beam, and then move the laser beam to capture the particle. These particles were trapped because of something called a scattering force that was found, and also a gradient force, which would then pull the particle into the laser. This acted like a spring, and there was no calculation to determine these two forces, but they were just observed and seen that the particles move in this way. And then another study was done by Daniel Smalley. This is very recently in 2018, where he created 3D volumetric images out of light with this optical trapping technology. He trapped a carbon-based particle in a 4 or 5 nanometer Blu-ray laser and manipulated this, not a 4 or 5 nanometer Blu-ray laser. He used many different lasers in his experiment. He primarily used 4 or 5 nanometer Blu-ray laser, but he used many different lasers as well to create these images, and he actually recreated that Princess Leia recording that we were talking about before in science fiction, which was pretty amazing. And finally, in the last primary study on this was done by Mark Lindsay, who's a student of Daniel Smalley, and he was looking to create something called an optical crayon. This would pick up a particle and then drag it through the lights, drag it through the air, and create images that a user would just in the air, not primarily coded or computer generated, but someone that you could actually move yourself. So this would be something that would be more user friendly. So I was looking at all this, and I was looking at a gap in this knowledge, and one of the things I was noticing was that all of the data on actual trapping wasn't provided, and what I wanted to know was how consistent was the trapping going to be if these optical trap setups would to be used in real life and applied for many people. So I wanted to know how exactly could the success be measured, and would it be a successful trap? So my problem was that these studies had a low cost and low power lasers, but don't really represent the reliability of the trapping. So my goal was to test these various size of cellulose particles which were used in these studies in a 4 or 5 nanometer Blu-ray laser, and to actually see if there would be a trap. And my hypothesis was that they would trap about 50% of the time, because there's a greater spontaneity between where the laser is and where the particle is dropped. So if the particle is dropped and it misses, there would be that chance that would happen. And so I thought about 50% of the time the particle would trap, and 50% of the time it wouldn't. It would just fall through. So the way I tested this is I created my own box for my own setup, and this block would block out all light, so it would keep everything constant and also keep the laser safe from possibly damaging any person that was using the setup. I used 4 or 5 nanometer Blu-ray laser, like I said before, with carbon-based particles. I also used a Pascal 550 universal interface to then control the current going into the laser, because if I did not control the current and the current spiked, it would burn out the laser and I wouldn't be able to use my setup. So I was very sure to keep it constant and not cause any ruptures to change any other variables. Then I would test for the trapping rates, and I would just drop particles through a little tube that I used to direct them towards the laser, and then I would see how many would trap. I'd know if it would trap if I'd see it in the laser propagation, or if I saw it on the bottom of the tube, which meant that it fell all the way through. Now, what I found was that none of the particles trapped. I did this about 60 times, and no particles trapped at all, which was unfortunate, but also revealed a lot of important things about the entire system. First off, the force of gravity was just way too strong to hold the particle, and that's what I determined. The particle fell right through, and the laser wasn't able to stop the particle at all. It was the force of gravity is way stronger than the gradient force that held it up. So that means that this laser was too weak, and I'm assuming that in my future research that we will use a stronger laser to then trap the particles, because a stronger laser would then have a higher gradient force than a weaker laser. So instead of having a 50 milliwatt laser that I was currently using, I'd use something more closer to 100 milliwatts, and I test that out. As you can see over here, on the top right, 100% were not trapped and 0% were trapped. For my future research, I was thinking about testing some other variables to try and see if that would change anything, altering the frequency, so not using 4 or 5 nanometers, but instead a different wavelength or a different frequency. Adjusting the aberration, so instead of using a spherical lens, use a different lens, or maybe changing the size of the spherical lens to change the where the focus point is. So maybe that was the reason the laser wasn't focused enough, so that's why the particle wouldn't trap. And then the final would just be using a more powerful laser. This is the last resort, because a more powerful laser is more dangerous. We'd rather use something lower power, but a solution nonetheless. So that's where my project is, and thank you for listening to my presentation.